Okay, so the first question, Gaston and Jordan are two budding chefs who unfortunately always misread the cooking time required for a recipe. For example, if the required cooking time is written as 1:32 for 1 hour 32 minutes, then Jordan reads it as 132 minutes, while Gaston reads it as 1.32 hours. So for one particular recipe, the difference between the times that they misread is 90 minutes, and we need to find what the actual cooking time is. So just for example, one of the times which they misread was 1 hour 32 minutes, which is 92 minutes. But then Jordan interprets this as 132 minutes, and then Gaston interprets it as 1.32 hours, which is 60 minutes plus 32 on 100 times 60 minutes. So in general, now, okay, sorry, 1 second. Yeah, so that becomes 79 and 1/5 minutes. So in general, Jordan interprets it as a time that's longer than Gaston's. And Jordan gets the hour bit incorrect and distorts that, whereas Gaston gets the minutes bit incorrect and distorts that. So if we get a general form for this, then we should be able to solve for the exact time. So if we say that the time, the actual cooking recipe time is given by X colon YZ, where X is the hours, Y is the tens of minutes, and Z is the units of minutes. So that means that Y can only be from 0, 1, 2, 3, 4, or 5. Z can be any digit, and X can also be any digit. But because we're looking at minutes and Y is the tens of minutes, Y can only take these values. So we know that Jordan interprets this as basically X, Y, Z minutes. So 100X plus 10Y plus Z minutes. Basically reading it as like a base 10 number. And we know that Gaston interprets it as X.YZ minute hours, which is 60X minutes plus Y on 10 times 60 minutes plus Z on 100 times 60 minutes. So that becomes 60X plus 6Y plus 3/5 of Z. Or maybe instead of 3/5, I'll write 0.4 Z minutes. Okay, and what do we have? So we know that the difference between their times is 90 minutes. And Jordan is always going to read it as a longer time than Gaston. And the reason that we know that is because each of these coefficients, 100, 10, and 1, are bigger than the coefficients for Gaston, 66 and 0.4. And because X, Y, and Z are all whole numbers, it follows for sure that Jordan always reads it as a longer time. So what we have to solve then is J minus G equal to 90. So it's convenient that I put everything in minutes, so I can just put 90 here. And if we do that, well, if I subtract the x's, I get 100 minus 60x, which is 40x. 10y minus 6y, which is 4y, and z minus 0.4z, which is 0.6z, is equal to 90. Okay. Now, I could now just divide everything by 4. So if I divide the left-hand side, oh, sorry, there are people in the chat. Yeah, so there happens to be only one possible time, x colon yz for this question, which gives them a difference of 90 minutes. And what we're going to see here is if I divide everything by 4 on both sides, I get 10x plus y plus I think I did something wrong here. So I think I meant 0.6 and I meant 0.4 here. Yep, it's definitely 0.6 for 60 on 100. And so when I do z minus 0.6z, I'll get 0.4z. 0.1z is equal to, and when I divide this by 4, I get 22.5. Okay, and now I've got it in a form that makes it kind of obvious what a solution could be. So writing it in this way, it's clear that I could make my z equal to 5 in order to get the 0.5 on the end. And it's clear that I could make x equal to 2 and y equal to 2. Now all of these values are allowed because they are whole numbers and y is between 0 and 5. So this solution gives 225. Remember, it's x colon yz as the actual recipe cooking time. And that seems to work perfectly. And if you're in the competition, you'd probably just be satisfied at this because you know that it works and you know that there is only one answer. But we'll just go ahead further to actually see why there is no other solution. I mean, you might not get to this point where the solution is so easy to see, so you will have to reason with why some of the other solutions that you might want to try won't work in the end. So why do the other ones not work? Okay. Okay, well, what you can do is from this point, if you can't see a solution, you can notice that the right-hand side is an integer. The left-hand side is integer times integer plus integer times integer plus non-integer times integer. And in order for all those things to add up on the left to give us the integer on the right, then that means that z would have to either be 0, so that the 0.4 just gets multiplied away, or z would have to equal 5. Or a multiple of 5, but if z was equal to 10, 10 is not a digit. So really the only possibilities for z are 0 and 5. So we can check each of these in turn. If z was equal to 0, then we would get 40x plus 4y equals 90. So we have a few possibilities for x to begin with. Can x be 0? No, because y has to be between 0 and 5, and the maximum for y is 5, meaning that the maximum for this is 20. So x can't be 0. X also can't be 1, because if x was equal to 1, then 4y would have to equal to 90 minus 40, which is 50, but we know that this term has a maximum of 20, so x can't equal 1 either. And if x was equal to 2, then we would need 4y to equal 90 minus 80, but then y wouldn't be an integer, so that's not possible either. And x can't be greater than 2, otherwise this would be negative. So from reasoning like that, you can get rid of this case. And this is going to give us the solution that we've already found, but we'll also see why nothing else is possible. So if this was the case, we'd get 40x plus 4y plus 2 equals 90. And again, we can do the same kind of reasoning. This has a maximum of 20. So immediately we can say x is not 0, and it's also not 1, because that would make 40x too small, and this wouldn't be able to get big enough to fill up the rest of the 90. So you can try x equals 2. And if x is equal to 2, then it's clear that y is forced to equal 2. And we already have that z is equal to 5. And obviously x can't be greater than 2, because otherwise this would have to be negative. So now we know that 2 hours and 25 minutes is our answer, but we also know that it's the only answer. Okay, so that's question 1 done. Let's do question 2 now.
All right, so maybe I have some comments. So,
Oh yeah.
So apparently there were 1,869 people who took the test this year, which I don't know, it feels kind of strange because the year before was like 2,400, right? So it kind of just fluctuated by a lot. And out of those 1,869 people, 1,415 people got this question correct. Yeah, so 400 people somehow got the question incorrect, or possibly only losing a mark or something. I think you might have to convert it into minutes or something as well. Yeah, I guess I also want to take this opportunity to just acknowledge that we have a very special guest here today. Mr. Singh Gao. So he was a participant of this year's AIMO 2019, and he got a prize. And so that's probably the only achievement I'll mention here that you can probably relate to. There's other achievements you'll probably relate to later. And I guess he has the distinction of having started the AIMO like Anson is doing in year 10. Okay, so he only did it his first time in year 10. So we've seen like Yasser and Haibing. Yasser started much earlier in like year 8. Haibing year 9, and Singh, he only started his first AIMO in year 10, but managed to get a prize. So so if you guys want to ask him questions, you can message him and stuff, and he'll probably be commenting. And maybe if we're lucky, he'll present a solution or kind of comment on some solutions, especially towards the end. So yeah.
It's the fun fact.
Did someone say fun? What's the fun fact?
Just a fun fact. I actually got the lowest score that's required for the prize. Pretty lucky.
So he was just one above. He was just one off the prize cutoff, I guess.
Don't play down your achievements, Sing. Okay, I'll get started with question 2 now, if everyone's happy to move on. I think Anson asked, what's the lowest score? And Zing said 28. Okay, I'll just get started with question 2 now. Okay, so this question says, an integer has 3 digits in base 10. Can everyone hear me okay, by the way? Or is... Okay, anyway. So an integer has 3 digits in base 10. When it's interpreted in base 6 and multiplied by 4, the result is 2 more than 3 times the same number when it's interpreted in base 7. What's the largest possible integer that has this property? So very wordy, but let's just write out what's happening. So we've got these digits. We've got these digits A2, A1, and A0 in order for the 3 digits in base 10. When it's interpreted in base 6 and multiplied by 4, so let's interpret this in base 6. Interpreting this in base 6 and reading it as a base 10 number, we get A2 times 6 squared plus A1 times 6 plus A0. Okay, that's interpreting it base 6 multiplied by 4. So 4 of this is the same thing as 2 more than 3 times the same number when interpreted in base 7. So that would be A2 times 7 squared plus 7A1 plus A0. Okay, and the question is, what's the largest possible integer with this property? So if we do some rearranging, this is 36, this is 49. So left-hand side becomes 144 A2 plus 24 A1 plus 4 A0. And the right-hand side becomes 3 times 49, which is 147 A2 plus 21 A1 plus 3 A0 plus 2. Okay, so these two are equal to each other. Can rearrange once again, and I'm just going to subtract the left from the right. We get 3A2 minus 3A1 minus A0 plus 2 is equal to 0. And we need to find the largest possible integer with this property. And since our number, our 3-digit number is this thing here, then we obviously want to prioritize maximizing the digit with the greatest place value, which is the first digit, A2, because it's got a hundredths place value. And then after that, we maximize this, which should force this to be something. And the question is, what is the maximum that each of these digits can be? Okay, so they're digits, but what digits are they? And we need to be careful and notice that, okay, base 10 allows all the digits from 0 to 9, but by saying that it is interpreted in base 6, that means that it can be interpreted in base 6. And for a number to be interpreted in base 6, it's got to use the digits from 0 till 5. And similarly, to interpret in base 7, you've got to use the numbers from 0 till 6, the digits, sorry. So since this 3-digit number can simultaneously be interpreted in base 6, 7, or 10, then that means that the maximum value of any of these digits is actually 5, which is the minimum of the maximums for each base. So that means that we have A0, A1, and A2 need to be 0, 1, 2, 3, or 4, or 5. So I've got this condition here and I want to maximize. So the first thing is, of course, I want to prioritize my greatest place value. So I want A2 to be as big as possible. So I'm going to say let A2 equal 5. Then we get 15 minus 3A1 minus A0 plus 2 is equal to 0. And now I still have a bit of freedom, so I can also let this equal to 5 because I want it to be as big as possible, which gives me 15 minus 15 minus A0 plus 2 equals 0, so that A0 has to be 2. So my number is then 552. And that's the biggest possible. Okay. Any questions? Let's go ahead and do the next question.
Hold on, there's some very interesting statistics for this question. Can you hear me?
Yeah, I can hear you.
So out of the 1869 people that did this test, only 218 got this question right. So there was like a big fuss, I remember, on the day about what it meant to be to interpret a number. I guess some people might have thought how to interpret the number in bases meant different things. So I remember Aaron getting this question wrong. Or at least I don't know if he got it wrong, but he said he spent like 2 hours on this one question or something, but yeah, so only 218 out of 1800. Wait, is there sound? Are you muted?
No, I'm here. Can you
Okay,
hear me?
I can hear you then. Okay, good.
Okay, great. Awesome. Let's move on to the next question, which is a geometry question. So I think I'll move this over here. There's a square ABCD with side length 24. So shockingly, I'm going to actually use the grid lines. Side length 24. Okay, and the square is A, B, C. Thank you. Okay, let P be the point on side AB with AP equal to 8. So it's a third of the way through. This is 8. This is P. And let AC and DP, thank you. AC and DP intersect at Q. And we want to find the area of CQD. So we want to find this region here. Okay, so what's good is we know the area of the square to begin with. That's always a good starting point. We also know exactly what the length is of this bit. It's 8, which is exactly a third of the entire side length. And we don't know exactly where Q lies just yet. But because we know some lengths, like the 24s, and we know some proportions, it would be really useful if we could establish some sort of similarities, because then we know how the areas scale. So let's begin by looking at these triangles. The small triangle, I'm going to just refer to this as small triangle throughout, and the big triangle. So it seems like it's a common theme for similarity to be in like the first 5 questions, geometry. Anyway, so these triangles are similar. And that is because, well, these angles are vertically opposite to each other. This side is parallel to this side in the square because it's a square, which means that by alternate angles, this angle is the same as this angle. And also this angle is the same as this angle. So same angles, and that means that triangle APQ is similar to triangle CDQ. And we know, in fact, what proportion they are similar in. Yeah. Okay, so we can actually prove that the heights are in the same proportion as the triangles. So we know that all the lengths in APQ are 1/3 of the lengths in CDQ, and that is because AP on its corresponding side, CD, is equal to 1/3. Okay, so one way that you can show that the heights are in proportion is just by looking at more similar triangles. So if I look at this triangle and this triangle here, they're similar to each other because these angles are the same with the white circle. And also this right angle is the same because they've been constructed so that they are altitudes to the triangle. And moreover, this is a straight line because we've got right angles at each end, and it's a square. Okay, so because of that, and because we know that this length to this length is in the ratio 3:1, that means the heights have to be in the same ratio. We know the green lengths are in the ratio 3:1 because of this pair of similar triangles. So yes, indeed, if we call this one H2 and this one H1, we have that H1 on H2 is 1/3. So I feel like this has come up a lot in the questions that we've done for AIMO, but as a consequence of that, the areas of these triangles are in proportion. And let's see why. So the area of APQ is, if we call this base 1 and this one base 2, it's half B1, B2. And if I divide that by the area of CDQ, we get half, oh, sorry, I meant height 1. And we get half B2 height 2. Okay, but we've already established that B1 and B2 are in the proportion 1/3, and that H1, H2 are also in the proportion 1/3. And these just cancel. So the proportion of the areas is 1/3 squared. So this is something maybe to just keep in mind, because it always happens with similar triangles. Whatever proportion the lengths are in, you square that proportion to find the ratio of the areas. Okay. So we definitely have enough information now to actually just calculate our areas. Oh, okay, actually we didn't even need this. My bad. Yeah, this was not even necessary, but I guess it comes up in other questions, so not quite a bad thing to learn. Anyway, the heights are in proportion, right? And the way we want to use that is to find what height 2 is, so that we can actually explicitly get the area of CDQ. So height 1 plus height 2 is 24, the entire side length. And again, that's because these altitudes together are a straight line. And this is 24. And we know that height 1 is 1/4 of that, and height 2 is 3/4 of that, because their ratio is 1:3. So that means that H2 is equal to 18, which means that triangle CDQ has area equal to half times base times height, which is half times 24 times 18, which is 216 units squared. And that is our final answer. Okay, so this was just an aside, which comes up in other questions, but wasn't exactly needed for this question. Okay, Michael, do you have any comments about this question? Question 3.
Yeah, so 1,094 people got this out of 1869. Maybe if we can go through this quickly, since we're kind of familiar with this question, I want to use it as like a way to introduce this technique. It usually doesn't appear in the official solutions, and I mean, it also is kind of, you learn this in school, but you don't use it on these kind of problems, and this might be a good example. You don't need to do it on this example, but it might be a good way to learn what we're talking about. So coordinate geometry, yeah. So maybe Yi can quickly, so maybe you can quickly kind of draw up what it might look like for coordinate geometry. So one thing that makes this kind of problem good for coordinates is the right angles in the square. So you know roughly where everything is. And essentially, so to do coordinates, you just basically need to pick a origin and the direction of the axes. And in this problem, you can kind of see it's natural to pick the axes to be sides of the square. Maybe the origin should just be the bottom left corner. And then it's just a matter of finding the coordinates of Q, right? So maybe should we go through this quickly?
Yeah.
Yeah, so I guess if people were willing to remember to times by 8 at the end, you could divide by 8 at the start, but maybe that's a bit risky depending on how good you are at remembering to do stuff.
So then Q would just be the intersection of two lines, and there would be no similar triangles. Okay, so I guess we could find out what the equation of this line is, which should be easy because it's
Yeah.
just a line through the origin. And so we only need to know what the gradient of that line is. And the gradient is always just the rise over the run, which is 24 on 8, which is 3. So the equation of this line is y equals 3x. And this one over here has clearly got a gradient of -1 because the rise and the run have the same magnitude and it's in the negative gradient direction. So we just need to know what to add at the end. And the y-intercept is 24, so it's very easy to read immediately that it's y equals -x plus 24. And then to find the coordinates of Q, all we need to do is find the point of intersection. So to find the x-intercept, the x coordinate of the point of intersection, just equate the y's.
Yes.
And then we get x equals 6. And then plug that back in, y is equal to 3 times 6, which is 18. So Q actually has coordinates 3, 18. And yeah, that's really nice because now we know that our height is equal to 18. And that's all we really needed for the area.
So to do the area of a triangle with coordinates, it's always going to be kind of easy because you can always just break it up into because it's lots of right angles involved, so you can, even if the triangle wasn't that nice, you could break it up into pieces that were that nice. Yeah. If you want, you could test out this formula. So the formula for the area of a triangle in coordinates is the determinant of the coordinates. So you can try it out.
Okay.
So
So
if you don't know what a determinant is, just kind of bear with us. It's just a formula that kind of summarizes how to do certain computations.
the determinant of the coordinates?
Yeah, so I think it's like, so I might have the order wrong, but it's roughly you put ones on the top row.
Right, okay.
Hello?
So one's on the top row. Yeah.
And then the x values. Man, let's try to do anti-clockwise. I'm not sure, but if it's negative, it's negative, but it'll be the same absolute value. So
Okay.
put negative x values. So so this is easy, I guess. It's q. It's just like, we can go from well, I don't know. We can start with one of them. Yeah. No, not negative. Just the x values. Yeah.
Oh, okay. Yeah.
And then the y values.
Cool. Okay, and then
So we actually had vertical lines for the determinant. Yeah. Okay. So see if we can evaluate this. So the formula is just expand about the first row.
So this times determinant of this, which is 0, minus this times determinant of this, 1 times determinant of that, which is minus 24 times 18. Okay, what is 24 times 18?
Just write 24 times 18.
Okay. And then plus 1 times determinant of this, which is 0. Okay.
Oh, maybe this needs to be
that's
divided by
double.
2.
Yeah, I think so, because it's like the determinant gives you the the parallelogram formed by.
Yes.
And so when you divide that by 2, you get the triangle.
Ah, good. Yes.
Yeah. And so obviously, yeah, this was indeed half outside of all of this. This was indeed the formula for our area.
Yep, see? No need to multiply.
Yeah. Cool. So that's something you could do too.
Yeah, so there's no question that should be completely like this. This is like a kind of like a emergency measure. Sometimes it even works better than the normal approach. All right, carry on.
Okay. Let's move on to the next question then. Okay, so probability question. Okay, so can everyone hear me okay?
Yes.
Okay, good. So question 4, it's this probability question. Jamie has a large bucket of 1,000 marbles equal size. I guess equal size just means that in terms of this question, what's important is that the probability of selecting any one of those should be the same. At least one is red and the rest are green. So you've got some reds, at least one, and the rest are greens. She calculates that if she picks 2 out at random, then the probability that both are red is the same as the probability that they're different colors. And then we need to figure out how many red marbles. And there's 1,000 altogether. So what we want to do is we want to express both those probabilities in terms of what's in the bucket. So if we just call the number of red marbles n subscript r, because that's what we're looking for, and the number of green n subscript g, which is also equal to 1,000 minus the red ones, then we can start to get expressions for each of those probabilities. So we have that the probability of selecting 2 red is the same as the probability of selecting 1 red and 1 green. Okay, so we're going to go with our classical probability formula, which is on the denominator, you get all the possible outcomes. So the number of possible ways to do this, select 2 marbles in general. And on the numerator, we have our desired outcomes. So probability of 2 red would be, on the denominator, how many ways are there to select 2 marbles at random from 1,000? So that is going to be 1,000 choose 2. And on the top, we have what's the probability, on the top, to select 2 red, our desired outcomes are when we select only red ones, but 2 of them. So the top would be, how many ways can I choose 2 marbles from all of the red ones? And there are NR of those. Now the probability of getting 1 red and 1 green is going to go very similar. Our possible outcomes remain the same, but our desired outcomes are going to be how many ways can I select one red one? And how many ways can I select one green one? And we multiply them together by the multiplication principle. So intuitively, we always know that n choose 1 is always n. So this numerator is nr times ng. And intuitively, it does make sense that there are that many possible pairings of the red and green marbles. So if we solve this, it's good that the denominators are the same, because to set them equal to each other, we only need that this is equal to this. So nr choose 2 is nr times nr minus 1 divided by 2. That follows straight from the formula, equals nr, okay. Equals nr times ng. Oh, okay, I'm suddenly in blue, which is also equal to nr times 1000 minus nr. So we end up just solving this. Have I done something? Nope. Okay, we end up just solving this like a quadratic. So if I multiply everything by 2, I get nr squared minus nr is equal to 2000 nr minus 2 nr squared, or 3 nr squared minus 2001 nr is equal to 0. So if I factorize, okay, so what are the solutions to this? Either nr is 0 or this factor is equal to 0, but nr can't be 0 because we know that there's at least one red marble. And so that means that 3 nr minus 2001 is equal to 0, which means that nr is 2001 on 3, which is 6, 6, 7. Okay, so with this 1000 choose 2 stuff, let's go back and talk again about this choose stuff. So this classical probability formula, I think everyone should be familiar with from school and stuff. Now with this choosing stuff, yeah, I think perhaps it's a little bit confusing because like these green marbles are all identical to each other, and these red marbles are also all identical to each other. So I guess it's a little bit strange that on our number of possible outcomes, maybe people might be tempted to write, there's only 3 of those, and those are the 2 reds, the 2 greens, and 1 red and 1 green. But it's not as simple as that, because of course the number of greens in there and the number of reds in there should influence which of these is more likely. So if there's heaps of green and compared to the amount of green, the red is negligible, then you'd expect to very rarely ever get these 2 situations. So basically it's important to distinguish between the identical marbles in this situation and consider them as different to each other, so that the number of different outcomes we can get is actually 1000 choose 2. So if I take the first green marble and I take the third green marble, that's different to if I take the second green marble and the fourth green marble. And in doing it like that, we can distinguish between these cases and weigh them according to how many greens and reds are in there. Okay. Okay, cool.
I wrote my solution like I think somewhere on the page. Is it all right?
Where is it?
It's very sketchy, like really, really sketchy.
Ooh, well, I mean, we got the same answer, so hopefully both of us are right. It's either we're both right or we're both wrong. Okay, so probability both read. Okay, let's go through this step by step. Okay, so I think that this works in the end. However, I think that doing this method might become problematic if it might become problematic if we weren't just talking about 2 marbles. So this is like basically 2 red and this is basically 2 green, right? Like what you've done here and the difference between what you've done and what I've done is, I mean, maybe it works. Like maybe this is just completely correct, but I'll just think out loud and we'll think about it together. But in general, when you do this times and you avoid any use of combinatorics like the NCR stuff, the difference between choosing rather than using multiplication is that this considers different orderings as distinct. So for instance, if I say count the number of ways to select 2 green marbles, and I give that to you as ng times ng minus 1, this counts the number of ordered ways to select 2 green marbles, so that selecting the first green marble and then the second green marble is not the same as selecting the second green marble and then the first green marble. So if you count the number of ways using multiplication only, then you're considering these 2 scenarios, these 2 different orderings as distinct from each other. But usually when we're just choosing marbles, we don't care about the order. So to account for that, we divide by 2 to account for that overcounting. And then this formula gives us exactly ng choose 2. Okay, so that's a general thing, which is true. However, maybe this ends up working in the end. I think in fact it does, because what you have is you have r times r minus 1 on 1000 times 999, but we know that that's equal to r minus 1 on 2 divided by 1000 times 999 on 2, right? And we know this to be nr choose 2 and this to be 1000 choose 2. So in fact, this probability is exactly correct. And this is correct for the same reason. But I would just caution against like easily interchanging multiplication like this for NCRs. And I would just encourage you to at least keep in mind whether accounting for order is going to affect the outcome of the question or not. So in this question, like if you account for order on the top as well as the bottom by not dividing by 2, it doesn't have an effect in the end because the divided by 2 just cancels out on the top and bottom. So yeah, this works, but just be careful about when you account for order and when you don't account for order. So in a sense, in this way of doing it, you've like distinguished between different orderings. But yeah, and then yeah, if you solve for that, then no surprise we get the same answer. But yeah, just be careful. Okay, any other questions about that? Or even about, yep.
803 out of something 1869. Got it right.
Okay. I'll just do question 5 as well, and then Ayush can take you through 6 to 9. So question 5, there's a beetle at the corner A of square ABCD. All right. So A, B, C, and D. And each minute the beetle can move along exactly one of the sides. So beetle can travel like from A to B, or B to C, or C to D, or D to A, or backwards. And that takes 1 minute to travel along one side. Okay, so for example, in the first 2 minutes, because traversing one side takes 1 minute, the beetle can traverse 2 sides. So it can be like ABA, or ABC, or ADA, or ADC. All of those are allowed. And the question is, how many walks can the beetle have from corner A to C in 10 minutes? So 10 minutes means we need to traverse 10 sides. 10 sides. And we need to start at A and end up at C. So if we want to traverse 10 sides, then there are going to be 11 locations starting with A, because from one location to the next is one side traversed. 6, 7. Okay, and we have to end up at C. So it's basically a question of count up the number of ways that a walk like this can happen. So obviously we've got multiple options for what goes on in between here. So if we just started to list out all the options, we would uncover a pattern. And the important thing we have here that restricts the choices we have is that the beetle can't traverse a diagonal. The beetle has to only go to adjacent vertices of the square. So from A, you can either go to B or D. From B, you can either go to A or C. From C, you can either go to B or D. And from D, you can either go to A or C. So it's interesting that A and C have the same adjacent choices. And that's obvious because A and C are opposite vertices. And so they should have the same adjacent vertices. And that's the nice thing about a square. Similarly, B and D have the same adjacent vertices. So B and D have the same adjacent vertices, and A and C have the same adjacent vertices. So if I'm going to just list out the options in terms of these adjacent vertices, then obviously from A, you can get to either B or D. I'm just going to write for shorthand, BD. And it's cool because B and D now have the same adjacent vertices, which are A or C. So no matter where you are, regardless of if you picked B to go to next, or if you picked D to go to next, you'd have the same set of possible next vertices to go to, which are the adjacent vertices A and C. Similarly, no matter whether you went to A or if you went to C, no matter which one you went to, our next set of possibilities is once again B or D. So you can see in this fashion, the options just alternate between the two diagonals. And clearly it checks out because from B and D, you can get back to C. So it's saying that no matter where we ended up, the last option has to be C to be counted. So the fact that no matter where we are, the next set of options is the same. So no matter B or D, the next set of options is A or C. And that happens for every single location is really nice. And that's why being a square is so nice for this problem. And it's nice because then I can just employ the multiplication principle and say that there's two options here and I can multiply that by the next two options because it's independent of which option I chose. And then I can multiply by that. So our final answer is that the number of paths is, yeah. Oh, wait, actually, I think it's 2 to the 9 because this is the first location. This is the 11th. Wait. Yeah, I think it's, wait, is it? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think it's 2 to the 9 because there are only 9 2s that we multiplied together.
He makes a walk every 10 minutes, every minute. So he makes 10 different options. So there's 10 twos.
But the
But
beta,
the last one is forced to C. So then.
so because the first one and the last one.
Yeah. I wrote 2 to the 10 and then I divided by 2.
Oh, and then you divided by 2. Okay. Okay, so that would have been slightly different to the reasoning I gave then. Okay, so it's 2 to the 9. Okay, cool. Yeah, it wouldn't have been so nice if it was like a pentagon or something, because then we wouldn't have this behavior where like no matter which vertex you choose, your next set of adjacent vertices is the same. So, but it probably would be similar in the end. Maybe they'd be different vertices, but the number of vertices would be the same. I guess the important thing is that no matter which path you take, like each of these options leads to C, and you can go to C. So that's the thing that made this question nice. Any comments or questions for question 5?
Yeah. So this question, 877 people got it right.
Out of
1869.
1869.
So more than the previous question.
Wait, really?
Surprisingly.
Oh yeah.
Last question was 1094. Yeah.
So Ayush will now go through 6 to 9.
Move 6 to 9 over. Is that recording for you guys?
I'm still recording on my computer.
Oh,
but I can't see your screen if that's what you're asking.
no. Did you get the record? This is meeting is being recorded thing.
Oh. I'm recording on my computer, so
Maybe pass it over to me.
okay, sure.